Okay, good afternoon. Yeah, so the exams are here. If you didn't pick it up, come up and get them after class. There is an answer key posted on the webpage under the exams link, so if you want to see the answers. And please do check over your tests because sometimes the TAs do make mistakes, and I can't catch them all. So if you do notice a problem with the exam, come and see me, and I'll take a look at it. Let's see. The average for the exam was 73, 74, right around that area, so not too bad. I want to caution you, though, the material that we cover in this class gets increasingly, I won't say more difficult, but there's just more material that just adds on. And it's not like you can take this exam and forget all those concepts, because they all build to the next level of the chemistry that we're talking about. So continue to keep up, and I think you should be doing okay. If you had noticed, I had activated a Learn Smart module for Chapter 4 through this Friday. If we don't finish Chapter 4 by then, I can always extend that too. So, but right now it's set for ending, I think Friday, right? Has anyone checked it? I'll have to double check. Yeah, something like that. Okay, let's continue then talking about Chapter 4. Last week, Wednesday, I started to introduce the idea of functional groups. In particular, we're talking about, in this chapter, two specific kinds of functional groups. That is, organic molecules that have a bond to an OH group, which we refer to as alcohols, and organic molecules that are bonded to halogens, fluorine, bromine, and iodine. And the reactivity of these groups, and with any functional group of the same class, reactivity is similar, or they have similar behavior in every molecule that contains that kind of functional group. And the reactivity of these particular two functional groups are dominated by their structural features. Partly being the electronegativity of these atoms. So, for example, when you have halogens, in this case, chloromethane, chlorine is significantly more electronegative than carbon, and so the bond is highly polarized. And you can see the dipole moment for chloromethane is 1.9 debye. Pretty polar molecule. And it's that bond between the carbon and the chlorine, which is the bond with which the reactions take place at, reactivity. It's the weakest bond in chloromethane, and that's where we expect things to happen. You can see the electrostatic potential map, where the red is more negative charge and the blue is more positive charge. That the end of the molecule by the carbon has more plus charge, and the end of the chlorine has more negative charge. Right? So the chemistry that we talk about will be due to the fact that the carbon has partial positive charge. So it would be, when we think about reactions and reactivity, it's going to be electrophilic. It's looking for electron density. Whereas the chlorine is partially negatively charged, it's going to be, well, chloride will be nucleophilic, but the bond will break. If it's polarized this way, the bond is going to break in that direction, pushing the electrons towards the more electronegative atom. And that's a general concept that permeates all chemistry, actually. Now, when we talk about alcohols as functional groups, yes, the bonds are polarized, and so this polar bond between the carbon and the oxygen has similar features as the carbon-chlorine bond. So the carbon will be partially positive and the oxygen will be partially negative. And so that bond has a possibility to break during reactions. Again, putting the electrons towards the oxygen. But alcohols also have another feature, and that is they have a proton attached to them, or hydrogen. And that hydrogen could come off as well. The bond between the oxygen and the hydrogen is also weak, relatively weak compared to the rest of the organic structure. And again, it's polarized from the less electronegative atom towards the more electronegative atom. And so that bond is going to break in ways which gives the electrons to the oxygen. So in this case, then, what would come off of this would be an acid or a proton, right? So it can act as a weak acid. At the same time, the oxygen having electron density can act as a weak base, and that also dominates a lot of the reactivity of alcohols. And I will say that carbon-halogen bonds are generally easier to break than carbon-oxygen bonds. Okay, kind of something we'll talk about a little bit more in the coming slides. Remember that alcohols also have this structural feature, that is when we have the lone pairs on oxygen and positively charged hydrogens that on those polarized bonds, that there can be some interaction between them. So for example, the hydrogen attached to one alcohol is interacting with a lone pair of an oxygen on another alcohol. This is what we refer to as a hydrogen bond. It's not a full covalent bond, not a strong covalent bond like we see in molecules that are intact and neutral, but it has significant energy. The strength of that hydrogen bond is about 5 kilocalories per mole. Really, really weak, but it's stronger than other intermolecular forces. So just electrostatic attraction or van der Waals attractions are usually weaker than 5 kilocalories. So it does provide a suitable interaction energy that is responsible for alcohols and water, for example, having higher boiling points because it's harder to separate them and put them in the gas phase. It takes more energy to do that because of this network of hydrogen bonding. Okay, and if you think about it in terms of acid-base chemistry, this hydrogen bond is sort of, I would say, a start on the way of a reaction towards giving the proton from an acid to a base, right? That's a transition between an acid to a protonating a base from an acid. Okay, and depending on the electronegativity of the atoms and the size of the atoms, we talked briefly about this concept of polarizability. So a lot of reactivity of molecules has to do with the ability of electrons to move, that is, bonds breaking and then bonds forming. So if something wants to form a bond, you have to have something positive, something negative. Those electrons have to move or shift to form a bond. So how tightly those electrons are held near a nucleus dictates some of its reactivity as well. When we talk about nucleophiles, that is something with electron density trying to form a bond to something that wants electron density, it's not as good of a nucleophile if it's holding onto the electrons really tightly. That is, if it's a small, very electronegative atom like fluorine versus a larger atom like chlorine where the electrons are more loosely held. That impacts that as well as the CCl versus CF bond strengths. And here you can see it's impacting in intermolecular forces and the ability to polarize molecules. So the tighter the electrons are held, the harder it is to even polarize them within a molecule. Okay, now this is where we finished on Wednesday, and I want to focus in some detail on this particular reaction. Okay? Organic chemistry really is the study of how we convert one kind of organic molecule to another through the use of changes in the functional groups and the reactivity imparted by the functional groups. So one of the things that we can do with an alcohol is to react it with an acid, a mineral acid like hydrogen chloride or hydrogen bromide, HCl, HBr, some hydrogen halide, and we get a reaction which takes place which substitutes the OH group for the halogens. And so what we end up forming in this process is a new carbon-halogen bond and a new hydrogen-oxygen bond. So notice this hydrogen ends up here with the OH group, and the halogen ends up on the carbon where the OH group used to be. So it's a substitution reaction. Okay, and we're going to talk in some detail about how this reaction proceeds. But first we should take a look at some of the observations about this particular reaction which have been noticed by researchers. So if you look at the difference when you do the reaction on the same alcohol with different hydrogen halides. So if you go down the trend from HF to HCl to HBr to HI, what we see is that we increase the reactivity. This is usually measured by looking at how easily or how fast the reaction goes and at a particular temperature. Okay? If it's a harder reaction or a slower reaction, you need to bring it to a higher temperature for it to proceed. So in terms of reactivity, HI is more reactive than HF. And it's the same trend all the way along. Okay? We also see some slight changes in the reactivity. If we keep the hydrogen halide the same, but then look at various substitution patterns on the alcohol, we see that there's a difference in reactivity as well. In this particular substitution reaction, the more substituted the carbon is of the alcohol, the faster the reaction proceeds. And so the best or most reactive substrate alcohol to do this substitution reaction is the one in which it's on a tertiary carbon. There are 3 alkyl groups attached. Okay, that's the most reactive. The least reactive is the one with no alkyl groups attached, just a methyl group. Which, by the way, is less substituted than a primary, and that's less substituted than a secondary. And so we see this trend in reactivity based on the structure, specific structure of the alcohol. They will all do this substitution reaction. So the characteristic reactivity or behavior of the OH functional group is the same, but they are proceeding at different rates. Okay, some are easier, some are harder, depending on the substitution substrate. Okay, are you following this so far? Here are some specific examples which demonstrates that explicitly. So if you look at the difference in these particular reactions, now I'm going from just a generic R group now and showing a specific alkyl group on the alcohol. Here we have an example of an alcohol on a primary carbon. And the reaction works. You react this with HBr, and you have to heat this up to 120 degrees. And the reaction will take place. And you can generate now the bromine. And notice I'm doing the lazy way of writing an equation for an organic chemist, which is the usual way. I don't care about all the non-organic chemical parts, really. I don't write the OH2O. And notice, I put the organic substrate to the left of the reaction. The reagents, which are important for the reaction, but not necessarily, I'm not highlighting that, I'm highlighting the organic parts here. I just put this over the reaction arrow, indicating the reagents in the reaction. But it takes 120 degrees for that to proceed with 1-pentanol. If you go to cyclohexanol, this is now an alcohol on a secondary carbon, so we would refer to this as a secondary alcohol. It's more substituted. You notice the reaction goes at a little bit lower temperature. 80 to 100 degrees, the reaction will proceed. And then if we go to 1-methyl cyclohexanol, now we're on a substrate which has a tertiary carbon. So the alcohol is a tertiary alcohol. And the reaction is going just fine at room temperature. Okay, so clearly the reaction is going faster, so we don't need as high temperature to make the reaction proceed. Okay. You don't necessarily need to use HBr either. So here's another example where you can get the same result, but not specifically put in HBr. As a matter of fact, in a way, we're sort of generating HBr in a different way, because what we have is we have a salt, sodium bromide. Okay, it has a Br minus group and an Na plus, and then we have sulfuric acid, which is a source of H plus. So it's not that we necessarily have HBr present, but that we have both elements. We have an H plus, so we have an acid, a Bronsted acid, and we have Br minus. Okay, and those are the critical things, that we have both present. They could be together in one molecule, or they could be provided in separate things added to the reaction. As long as they're both present, the reaction works. Okay, so if you take a look at all these examples and think about all of that, those observations in the data, you should be asking yourself now, how is this reaction actually proceeding? What's going on? Okay, what is making the CO bond break and making the CBr bond form? Okay, if you just take an alcohol and heat it up to even 100 degrees, you're not going to break the CO bond. Something else has happened. And chemists describe or explain how reactions proceed by talking about the mechanism of the reaction. Okay, so originally I wrote the overall transformation. Alcohol plus hydrogen halide gives alkyl halide plus water. Okay? That tells you what happens overall from the starting material to the product, but it doesn't say how it got there. And how it gets there could happen by many different pathways. So a reaction mechanism is what we refer to as the detailed step-by-step description of all the transformations, showing each step in the reaction, if it's more than one step, and any intermediates that are formed along the way. Okay? And when we hypothesize a reaction mechanism, all of the observations about that reaction must be consistent with each of those steps we've proposed. Okay, so let's think about this process, this overall process. When we really want to think about elementary steps of a chemical transformation, we need to keep in mind some of the things that we're talking about and thinking about reactions. One of those is what we call thermodynamics. Okay? Thermodynamics is looking at the overall change in energy in a reaction from one side to the other. And we've talked a lot about thermodynamics, but not really explicitly like this. Right? We talked about acid-base chemistry, right? Equilibrium. So is a reaction going to lie on one side of the equilibrium or the other side of the equilibrium? And what is the ratio, right? Let's see, you know about equilibrium constant, or acidity constant, which is basically an equilibrium constant for an acid-base reaction. That's the ratio of the products over the reactants, right? Or how much is there, the concentrations of those. And that will change depending on the difference in energy between the two. The reactions will proceed easily downhill in energy, then it's delta G, or Gibbs free energy overall for the reaction, there's equilibrium constant, is negative. That means the energy is released in the process, and it's an exothermic reaction. If your products are higher in energy than your starting materials, then it's a reaction which is going what we refer to as uphill. The Gibbs free energy, or delta G, is positive, and energy is needed to be absorbed in that process. Okay? So remember those key things from general chemistry. Now, we can estimate the overall delta G, or Gibbs free energy, for a reaction process by looking at just the heat of reaction, or enthalpy. The enthalpy is given by delta H, and it's just referring to the energies of the bonds. So you're comparing bonds broken versus bonds formed in the overall process. Sometimes referred to as heat of reaction. Okay. The other part of Gibbs free energy here's a constant temperature, whatever temperature we're at, and entropy. Entropy, of course, is a measure of disorder. So if you have large changes in entropy in a reaction, that might be really important. But in most cases, we're not changing the entropy a whole lot. So we can estimate, the overall reaction equilibrium of a reaction based on looking at just the bond enthalpies of what's broken and what's formed. Okay? This, again, is referred to as thermodynamics when we're considering the overall energy change in a reaction. Okay, so bond enthalpy, or the bond energy, we mentioned this before, something we refer to as the bond dissociation energy. This is the bonding energetic profile I showed you before for hydrogen, H2. So the energy of a bond is the energy necessary to break apart the atoms homolytically, that is, each one gets an electron, as opposed to a heterolytic bond cleavage where both electrons go one way or the other. That's what is defined as the bond dissociation energy. And it's those energies that are, and they're different for each bond, kind of bond between atoms. It's the change in those energies, both broken and formed, that give rise to the overall change in the enthalpy for the reaction. Okay? So let's take a look at this particular reaction we're talking about. Substitution of an OH group on a carbon for, in this case, the bromine. And notice what's happening in this process. We are breaking a CO bond, and we're breaking an HBr bond. So on the left side of the reaction, those bonds are being broken. That is, in order to break bonds, that has to absorb energy. You have to put energy in to break bonds. And that energy that's required is the energy associated with that bond dissociation energy. Okay? Now the products on the right side of the reaction are a bond. We formed a new carbon-bromine bond, and we formed a new hydrogen-oxygen bond. Okay, so if we just calculate the differences in the bonds broken and the bonds formed in terms of the energy, you can look these up. There are tables and tables and tables of bond dissociation energies for all different kinds of bonds. So you just look up a CO bond. It's about 350 kilojoules per mole is the bond dissociation energy for that. And an HBr bond is about 366 kilojoules per mole. So in order to break all the bonds we need to break on the left side of this equation, we have to put in 724 kilojoules of energy for each mole of our reactants. Okay? And then the products are formed, and forming bond is release of energy. And if you, again, look up what the bond dissociation energies are for a CBr bond, it's 285 kilojoules, and an HO bond is 465 kilojoules. So in the bond forming processes in this overall reaction, we've released 750 kilojoules of energy. Okay? So overall, if we just add up the bond dissociation energies, the change in enthalpy for this reaction, the energy you put in, 724, minus the energy you get out, 750, that leaves 26 kilojoules left over that are coming out of the reaction. Okay, delta H is negative. That's pretty close to what the delta G is. Okay, so energy is being released in this process, in this overall process. So is it exothermic or endothermic? Exothermic, right. The products are lower in energy than the starting materials. That's what this is telling us. Okay? Products in this case are low, and we can estimate that. It's a pretty good estimate. It's not perfect, but it's pretty good, just looking at the changes in the bond energies that are broken and formed. All the other bonds are staying the same, so we don't even need to worry about that. Okay? So now this analysis of the thermodynamics, or change in the energy of the reaction, tells us which side of the equilibrium the reaction lies on. It tells us whether that reaction is favored or disfavored, right? But it doesn't say, again, it doesn't tell us the pathway to get there. We still don't know that pathway, okay? It could be a long pathway through many steps, or it could be just one step to go from starting material to products. So all this is saying is that we have, if you can, let's say energy in this direction. You have starting materials at this point. You have your alcohol and your HBr, and your products are lower in energy. So overall, you have a negative delta G, or negative delta H, since we've calculated that. Okay? We just know that it's lower in energy. But what's the path? The pathway is important because that's going to tell us a lot about how fast a reaction will proceed and how much energy you really have to put in to get over that path. Okay, I like to use the analogy. Does anybody like mountain biking? I guess there are no mountains here. Right? If you want to go from point A to point B, and you got to ride through Fargo, it's going to be pretty easy. But if you're out in Colorado and you have to go over the mountain to get from one side to the other, it's going to take you a lot longer, and it's going to take a heck of a lot of energy, right? That's kind of like what happens in chemical reactions. Okay? Any chemical reaction, and in this case, even if we have a reaction which overall releases energy, that's the thermodynamics, the delta G, the difference in energy from starting material to products. But the path could be many things. In this case, we can describe this on what we refer to as a reaction potential energy diagram. So to give you some idea about what these axes are, energy is in this direction. Okay, so energy is in that axis. Along the reaction path are really all of the structures of the reactants. And just use something A here generically and B as products. But A has some structure, and A could be more than one molecule. It could be 2 molecules or 3 molecules or whatever. The overall structure, and as the structures change from starting material to the products, okay, bonds are breaking and bonds are forming. You can envision this as a continuum of structure changes as you go from A to B. The structural features will change in energy. At some point, usually what happens is you start rising in energy as you're starting to break bonds and make bonds until you reach some plateau or some highest point. I guess it's not a plateau, it's just an instant point. You reach some point, which is the highest energy, and then as your molecules are reorganizing and bonds are forming and breaking, you get to the products, you go down in energy. Okay? So the difference from your starting materials to the top highest energy point is what we refer to as the activation energy. You have to have, no matter what the difference in energy from your starting materials to your products are, if you have a really high mountain, there's a minimum amount of energy you need to put in to get over that mountain. That's the activation energy. Okay. Another point of terminology is that the structural feature, or the structures of the reactants, at that highest energy point, we often refer to as the transition state. And since it is the highest energy point, it has no lifetime. It doesn't exist except for an instant in time. Because once you reach there, it's going to immediately go downhill the other side or back this way. Okay? So it's not something that you can isolate. It's not an intermediate. It's not a molecule you can observe or a structure you can observe. But it's useful to have some idea about what that might look like when we think about energy changes. Okay? So this is an example of a reaction energy profile diagram for a reaction which is one step. Okay? Starting materials, activation energy to climb the barrier, and then down to the products in one step. Okay? Reactions don't have to be just one step. Reaction mechanisms can proceed by multiple steps. So here's an example of a similar kind of process, but it's not just a straight path. Okay? You have some starting materials, your reactants A, okay, and some products, which I put C here just because I have another step along the way. But along the way, there's a minimum, a local minimum in that energy diagram. That's what we would refer to as an intermediate. That could be something that could be observed. It might have some lifetime, be able to detect it in some way. Okay? The transition state on the way there you could not detect. And notice in this case, a two-step reaction, you're going to have sort of two hills to climb. Okay? You got to go from A to B first. B happens to be higher in energy than A. But overall, we're going down to C, which in this case, for the purpose of this example, is also a negative delta G. Okay? Now, with having two hills and two maximum energies of those hills, then you have to think about the comparison. So the difference between the starting materials and that transition state for each of those, they're not the same. Okay? One hill is going to be higher than the other. In this case, the first one is higher. Sometimes it's the second hill which is higher. Regardless, how fast you can pedal your bike over the mountain is going to depend on, not on the lower one, but it's going to depend on whatever is the highest point. Okay, so that's the minimum amount of energy you need to get. This energy, which is lower, you know, once you get up to here, there's plenty of energy to go all the way down. Okay, but you got to get up to here first. So the time it takes, or the amount of energy it takes to reach the highest transition state in a multiple step process, or in the chemical transformation, is the slowest step. Okay? The slowest step in a reaction is always the one with the highest activation energy for that particular transition state. Okay? This is what we refer to as the rate determining step. See, now we're talking about more than just A to B to C. We're talking about the pathways they get there. Rate determining step, the slowest step in the reaction, or the step with the highest energy difference from starting materials to the transition state. Okay. So if you have a process which does have an intermediate B and before you get to C, it's not the reaction from B to C in this process is going to be faster than the reaction from A to B. So it doesn't matter what the rate of B to C is. What matters for the slowest, the reaction can only go as fast as its slowest step. Okay, and that's the point. And having an idea about which step in a reaction is the slowest one or the highest energy one, that can tell us a lot about mechanism and make sense of data that we observe regarding things like why does substitution on the alcohol matter for the rate of the reaction. Okay. So here's some of these terms I've been talking about. Activation energy, the energy required to overcome an energy barrier or to get over that hill. Rate determining step, the slowest step in a reaction, the one with the highest energy barrier. The transition state is the structure of your reactants at that transition state, which doesn't exist except for an instant in time. And one thing that I didn't mention yet, the structure. Since we can't really observe it, we can only really calculate what the structure might look like. But we can make some guesses as to what it might most closely resemble. And this is what's referred to as Hammond's postulate. I think your book states it slightly differently. But really, in a nutshell, Hammond's postulate says that a transition state and the structure of your reactants at the transition state is going to be most similar to whatever on either side of that hill is closest in energy to it. Okay. So, and let me just say, for example, if you have some starting material A and you go up to some intermediate B, okay, A to B, right? The transition state structure here is going to be more closer to B than A. If it's the other way around, if this process has A higher than B, okay, the transition state structure here is going to more resemble A than it will B. Okay, that's really what Hammond's postulate is all about. So any questions on any of these terms and what they mean?
In the rate reactant step, is the term mechanism and reaction interchangeable?
Mechanism and reaction, probably. When we talk about reaction, we're talking about the overall reaction, generally. And when we talk about mechanism, we're discussing the pathway to get there. And we often say the reaction mechanism to make that even more confusing. Okay, so let's think about then what this process might be doing. Okay, can we propose some process by which the bonds break and the bonds form? So based on what you know from your chemical intuition, you've been studying chemistry now for at least a year and a half, right, or a year and some. What might be the first thing that could happen between the reaction of an alcohol, here alcohol, and a hydrogen halide? What is the reactivity behavior of these? Okay, we know that HBr or HCl, we know what kinds of reactions that does generally, right? What does it do when you put HCl in water? H2O plus HCl. What happens when you dissolve HCl in water?
Ions are formed.
Ions are formed by what process? What's happening? It's an acid-base reaction, right? You have water being a base, and HCl, the proton of HCl, is the acid. You form a hydronium ion, okay, plus Cl minus. Hopefully you know that process, right? That's what happens when you dissolve HCl in water. So what do you think might happen if you take an alkyl alcohol and react it with a hydrogen halide? A good guess as a first step is going to be transferring a proton from the HX to the OH. Okay, that's a pretty good first step. So think about that alcohol is a base, and this is an acid. So you can protonate, transfer the proton. Let me just draw it here. Okay. That will usually acid-base reactions are in equilibrium. So now we've protonated. Is that big enough? Okay. We've protonated. Okay, and that's most likely happening. And I'll tell you right now, this is known to happen, and it happens quite rapidly back and forth. And so what we've now done is change the nature of the carbon-OH bond. Okay, so notice in the alcohol we have C bonded to OH. It's a relatively strong bond. That bond needs to break in this process. By making the oxygen with a formal plus charge, we've now changed the nature of the reactivity. So this bond between the carbon and the oxygen is now weaker. Okay, and that's the things you need to think about when you're thinking about how reactions work. What is the nature of the reactivity and how does it change when we do things like this? So protonation of the alcohol makes the bond weaker. Why? Well, think about the electrons in the bond from carbon to the oxygen wanting to break. So push those electrons to the oxygen to neutralize the plus charge. Okay, and that's going to then form some carbon group. I'm just using R here generically. Some carbon group, which now has lost electrons. So it has the plus charge, and it's what we would refer to as a carbocation. Okay. And we still have, and then the other thing we formed here is water, because water came off as a neutral species by taking those electrons from the bond. Okay, look, there's one product in the reaction. So we can see how the water was formed in the process. Now we got to think about how that's formed. So how do you think that might form? Yeah, we have a carbon with a plus charge, a carbocation, and we have this X minus that we formed. Okay, X minus is a nucleophile, it has electron density. The carbocation is an electrophile, it wants electrons back. And so X minus will donate and form a bond to the carbon and generate the other product. So among all my scribbles, I have this better presented on the next slide, but among all my scribbles, how many steps do you see in this process? How many reaction steps? That is, the first step is the alcohol being protonated by the acid, so that's step one. That's feeding back a little bit. The breaking of the CO bond to form the carbocation in water, that's step two. Okay? And then X minus reacting with R plus, that's step three. So there are 3 steps in this reaction. Okay, and each one of them makes some sense chemically. If you think about where electrons are and where they're moving and where they're changing, that all has to make sense too. So if we take a look at this overall, I have all 3 steps listed on the next slide for you. Step 1, protonation of the OH group by the acid. In this particular example, HBr I put here. And a few more details about this. When we have 2 different molecules which have to interact in the step, that's a reaction step which we refer to as a bimolecular reaction, 2 molecules. Okay, that's necessary for this. And this is a fast process in this reaction mechanism, and it's actually an equilibrium and it goes back and forth quite rapidly. So what do you think the activation energy might be compared to something else? It's going to be small relative to the second step. The second step only involves breaking this CO bond to form the carbocation and water. Okay, that's a unimolecular reaction. It doesn't depend on anything else. It only depends on that protonated alcohol species. Okay? In this reaction, actually, this has been determined and measured as the slowest step in the process. That's the one that's going to have the highest activation energy barrier. Okay. And then the third step in this reaction, also a bimolecular reaction because we're combining 2 molecules, a carbocation intermediate and a bromide intermediate, and forming a bond. And that's faster than that middle step. Okay, so 3 steps in this process. And we can take a look at those all and look at each step in their energy profiles. This is the protonation of alcohol. If you calculate the change in energy in the reaction, the thermodynamics of the process, what you see is that the reactants here, alcohol and HCl, this actually happens to be tertiary butyl alcohol. It's an alcohol and a tertiary carbon. Protonation of that is lower in energy. So overall, the delta G is minus. This is expanded in, but the energy is not that different. Notice there is an activation energy barrier. Every reaction generally has at least some activation energy barrier, even if it's small. And this is trying to depict what the transition structure might look like. So it should be closer to the starting materials than the products in that step. The CO and OH bond are still in, they're similar. But what's happening is we're starting to form a bond, beginning to form a bond between a lone pair of oxygen and the hydrogen of HCl. So this is bond forming on this left side. At the same time, the bond between H and Cl is breaking. It's not fully broken in the transition state, but it's breaking. Okay? And so that's sort of depicting something which we can't really directly observe because it only exists an instant in time. The transition between there to there at that highest energy barrier. Okay? The second step. Once we form that intermediate, that protonated intermediate, the second step now is the breaking of the CO bond to form water and the carbocation. Okay? This is a largely endothermic process. The protonated alcohol down on the left is low in energy. The carbocation and water and Cl minus, the products of that step, are much higher in energy. And that makes sense, right? We have a molecule which doesn't have an octet now. The carbon of that, where the alcohol came off, is missing electrons. It has a plus charge. That's going to be high in energy relative to the starting material. Okay? And there's a very significant activation energy barrier here. Okay? And in this process, it's a unimolecular process, so this chloride here hasn't changed at all. It's not involved in the transition state, although it's present in the reaction. The only thing that's happening is the CO bond is beginning to come apart. Okay. We will talk a lot about structures of carbocations. This happens to be a tertiary carbocation with an empty p orbital on it. That's then carbocations are sp2 hybridized and have a planar structure. Okay, and that's going to be important when we start to talk about the differences in substitution patterns. And then the third step, if you look at the energetics of the third step, we go from reactive species now through an activation energy barrier down to stable products. And we know those are even lower than our starting materials. Okay? And what's happening in this step is that the plus charge on the carbon is now bonding with the electrons being donated from the chloride. A bimolecular reaction in the transition state, it involves both the carbon group and the chloride group coming together. So this activation energy depends on both of them and their concentrations. And that forms now the product, which is down here in energy. So if you put that all together on one energy diagram, this is what it looks like. Okay? That's everything to scale now in terms of, at least better scale, in terms of the energetics. So this step here, the protonation, since you have to put in this much energy for the reaction to proceed at all, there's plenty of energy for this to be going back and forth, right? That's why it's in equilibrium. That initial equilibrium, and it's fast. Okay? Once you get up here, then you get to this intermediate, and it's easier to go downhill this way than it is to go back this way. So the overall energy profile encompasses each of those three steps. Notice there are 3 hills at different heights, 3 different steps. The slowest step is this middle one, the formation of the carbocation by losing water. Okay, on Wednesday we're going to talk more details about why the substitution on that group matters and changes the activation energy, makes the reaction faster or slower. Okay.